So we've covered how to do an independent t-test, right? Where we have two groups and we're comparing those two groups on some continuous variable, our outcome variable, our dependent variable. Now, what do we do if we have three or more groups? As you can maybe remember from the inferential statistics section of our course, when we have three or more groups and it's separate groups, they're not the same people doing all three conditions, then we do a one-way ANOVA. It might also be called a one-way independent ANOVA. And the ANOVA tests whether or not there are differences among three or more groups. You might have been wondering why not just conduct multiple t-tests. As I describe in the chapter, if we do multiple t-tests to compare the differences among all the combinations of the groups, it actually increases our overall type 1 error. And so it's more likely that we're going to find a statistically significant result by chance alone, that we're going to have false positives. That chance of having a false positive is going to go up as we conduct more tests. So we want to be very careful about how many tests we're performing, being really critical about which tests we're performing and having those clear hypotheses ahead of time. Otherwise, we're increasing our error rate in our studies. So that's why we do things like pre-registration. That's why we're very clear, or try to be, or I recommend we be very clear about what we're doing, why we're doing it, exactly what we're going to do. Because otherwise, we're just going to increase the likelihood that we're kind of fudging around with our data and getting it to a point where we may not be as confident in our results as we would like to be. So we are talking about the one-way ANOVA today. So we're working with the, what data set are we working with? I need to find it in my chapter. Well, let's find it. Okay, so open, it's one of these from the LSJ data set. It's probably ANOVA. That's repeated measures. That's not it. I think this is it. This is it. Awesome. Okay. So in this data set, we have a few variables that we're going to be working with. There's some extra ones we're not going to work with. We have the ID of the participant. So this is actually importing incorrectly. So we actually want to change that to ID. Good. We have drug. They are either in the placebo, anxiety-free, or joyzepam conditions for the type of drug that they're taking. And they're either receiving therapy or not receiving therapy. And then we're measuring their mood gain. Then these are just set up that, and actually I think it's got, these are set up if the drug equals anxiety, I don't even know how to pronounce that, the anxiety-free drug, it's coded 1, and if not, then it's coded 0. So if we go back and look at this compared to this, if it's this, then it's 1, and if it's anything else, it's 0. So it's just saying 1 or 0. Are you getting the anxiety-free or something else? The joyzepam or something else? The CBT therapy or something else? Those are just some, I don't know how to describe it, but you can see how it's based on these two variables. So we could actually delete these and not lose anything, but this is fine. Now, real quick, if I had you compare no therapy to CBT on the amount of mood gain that they get, what statistical test would you perform? Think back. Which would you perform? Drink my coffee while I wait for you to think about that. So if you answered the independent t-test, then you are correct. We are looking at two separate groups, right? We have 9 people in one group and 9 people in another group. They're not the same people. And we're comparing on our continuous outcome. That would be an independent samples t-test. Now, if we're comparing the 3 different drugs on mood gain, what would we perform? Which statistical test would we perform? Feel free to pause if you need more time. So if you answered the one-way independent ANOVA, then you are correct. So because we have 3 groups, we want to do the one-way ANOVA. Now, technically, you could compare therapy versus no therapy using a one-way ANOVA. And I described that a little bit at the end of the chapter about how it's mathematically the same. but technically independent t-test is a bit more of a correct answer there. So because we are looking at the Way ANOVA today, we're going to compare which drug performs better in increasing mood gain. Okay, so we've got 3 groups. We're going to just look at our data real quick. It's pretty easy because we only have so much information, but let's look at our outcome variable. Let's just go ahead and get some plots with that. Okay, it doesn't look greatly normally distributed, but we'll look at it over. Got a decent mood gain. Okay, and we could look at this and do frequency tables as well. And it looks, we already saw this, right? It's a small data set, but equal groups of within each of the 3 drug conditions. We could also instead do a split by and look at it split by the 3 conditions. While I'm here, a reminder that you should have your number format set to 2 decimal places and your p-value format set to 3 decimal places. Just a reminder there. And if you're wondering how I got these grays, I have my color palette be gray. There's a bunch of different other options, but I like gray because when we're putting things into like things that are going to be printed, a lot of us don't pay for color printing, and so a black and white gray palette is going to just be nicer and a little less expensive. So that's my only reason there. Okay, we need to check our assumptions. They are the same assumptions as we have in the independent t-test. The first is that our dependent variable is normally distributed. So let's just go back here and check whether it's normally distributed. That doesn't look great, but we also have a really small sample size. Let's also, don't forget to check skew and kurtosis and Shapiro-Wilk and the QQ plot. Okay, so Shapiro-Wilkes looks good, not a problem there. Skew, we can run, I'm going to do Windows key R. That gets me to open, and I could do calc for calculator. Excuse me. Okay, and then we're going to divide our skew by our standard error of skew, 0.16 divided by 0.54 equals 0.29. We are good there. And let's say do the same thing with kurtosis, 1.26 divided by 1.04. I'm ignoring the negative because we're going to take the absolute value anyways. That's less than 1.96 as well. So all of this plus our QQ plot suggests it's pretty normally distributed. That being said, we have a really small sample size, so it would have been nice if we had a bigger sample size here. Okay, so overall, this is all concluding that we have met the assumption of normality. Let's go ahead and just run the test because that's the easiest way we can get to the Levine's test. So to run the Way ANOVA, we're going to click ANOVA, and this is where I'm very adamant. Don't run the Way ANOVA. I'm going to just show it real quick. Look there's not very many options here. So I want you to run the ANOVA test. There's lots more options here. So don't run the Way ANOVA. Go to ANOVA. Don't run the Way ANOVA. Go to ANOVA. I will be checking that. There will be ways that I'll know if you've clicked the right one. One being just the heading, but there's a few other hints that will give me like, you didn't check the right one, right? Reminder, you can always go back to your analyses, and if you end up going into your data, you can always come close out and you're doing stuff. You can always come back, just click on it. You don't have to run the analysis again. I'm just going to delete this because this is wrong, right? Delete that analysis. Okay. So we have our ANOVA. What is our dependent variable? Gives you a little hint, continuous variables. So we're going to put mood gain in there, and we're just looking at drug. So we're going to put that in there. Okay. Let me go back to my little chapter, remember what I need to put in here. So I've moved my stuff here. I want my omega squared effect size. Why not these two? Because this is a little less biased of an estimate. It's just a better estimate of our effect size overall. So I like to choose that. You could probably check these and note that they're fairly similar. That's fine. But we're just going to do omega squared. We're going to ignore model. This is if we have more complex models. For a Way ANOVA, it's not complex, but for complex like factorial models, you might need to get into here. We're going to go to assumption checks. We're just going to check them all. I want to note something real quick. Our Shapiro-Wilks is slightly different when we check it here than compared to up here. Why that's the case, not entirely sure. Haven't really explored. It gives us the same like inference, the same result. So I'm not worrying about it too much, and I don't think you should either. So we'll check, we can actually uncheck them. We've already tested that. So we'll just leave the homogeneity test to get our Levene's test. So let's pause there real quick. We'll check our second assumption of homogeneity of variances, and our p-value is not statistically significant, and therefore we have met the assumption of homogeneity of variance. We have normally distributed data. We have equal variances among the groups. We are good to go with running the one-way ANOVA as opposed to the Welch's F test. Okay, good. We've checked all those. We're going to ignore all this just for a second. We'll come back to this. This is the second part of the reading. So first is just the overall ANOVA, and then the second would be looking at the group differences. So we'll come back. But first, let's do estimated marginal means. We're going to move this over. You can either drag it or do the arrow. And this will just give us the marginal means of the data. Again, it gives us not a great data visualization. So I'm just going to, we'll leave it there. But I also like having my tables because then I've got my statistics, my mean and standard error. And I can ask for the confidence interval or the standard error, either one for the error bars, and I could change it to be the observed or to add the observed scores. Actually, that's a little bit better. I'm not too upset with that. That's not, I think this is new. Like every once in a while they add little things, and when I first made my textbook it was in like 1.8 something. Now we're at 2.0. So little updates. That's awesome. So this is actually a not too bad plot. I wouldn't be mad with this. I'd be okay with this. Oh, and you can ignore that. Okay, so we ignore the save. That's a new feature as well, something that comes with the regression usually. That's awesome. So now we have our descriptive statistics here as well. And you'll note that they should match what we have up here. If I were to split by drug, and I'm just going to do across rows just to look at it a little easier. 0.72, 1.48, 0.45, 0.72, 1.48, 0.45. So those all match. Okay, so let's pause there and interpret our results. Let's go back to our overall ANOVA test. Now there's some math behind this. If you're interested in that, comment. I will add some information about that, about how to how do we get to this overall F. And it has to do with all of this, and it's actually not too bad to calculate, especially with a small data set like this. But again, for most of us, even myself, it makes my eyes glaze over and I'm just like, whatever. Like, if we can interpret this correctly and perform it correctly, then the math underlying it, we can save that for the statisticians, the mathematicians. We're going to be the applied researchers. Okay, our p-value is statistically significant, is less than the typical alpha of 0.05. Therefore, we have a significant difference among our three groups. And we would write this up. I'm just going to move this over real quick. We would write this up something like this. Or this, the two options. There was a significant difference in mood gain across the three drug conditions. Remember, italicize our F, parentheses, and now we have 2 degrees of freedom, 2,15. So we do the within subjects. So there are 3 groups. So 3 groups minus 1, that's our degrees of freedom of the number of groups, comma, the number of people in our sample size, and it's number of people minus the number of groups. So 18 minus 3 is 15. So that's one, just so you know, this is something I sometimes look at to be like, what was my sample size and how many groups do I have? And so if I see something in a write-up and they're like, oh, we tested an ANOVA among our 5 conditions and their degrees of freedom right here is 2, then I'm like, ooh, something's wrong here, right? Those are little clues for me. Just like if they say we had 100 participants and there were 3 groups, and then they say the degrees of freedom is 90, I'm like, oh, you're missing some data there. Something's wrong here, right? And so those are little clues for me about like, are they actually doing things correctly? Just so you know, there's also ANOVA calculators online, so I could test whether what they say in terms of their their mean group, the like actual descriptive statistics in the groups, or even just their F-test if like they reported it correctly, because there's actually been some research that people will report the wrong p-value for the associated F-test. How they do that, not entirely sure, but maybe it's just user error because people are usually typing up their results. But it's something that we can always check and make sure that we're doing it correctly. Okay, let's move on. So we've written this up. There's a significant difference in mood gain across the three groups. Where's the difference, right? And so you might go like, oh, let's just look here. It looks like joyzepam does better than both of these two. But is that correct? You're just looking at the plot. We want to know statistically, is that the correct inference? So, sorry, I'm moving this over. I'm going back to my next chapter. This is the finding group differences stuff in our reading. There are two ways we can check for group differences among our groups in the ANOVA, because the ANOVA just tells us, is there a difference, not where the differences are. There are two different types of things that we can do. We can do either planned contrasts, which are found here, and you'll see that there's a few different options here, and I describe them in the textbook. I might have a specific planned contrast ahead of time. For example, joyzepam maybe is my drug. I want to see if my drug does better than the existing drug, anxiety-free, compared to the placebo. And so for that one, I would do, let's see, I always have to remember which one it is. I think, I would probably have to actually change my, I would probably have to change the order, but because I want to compare joyzepam to anxiety-free and joyzepam to placebo. Oh, here we go. We want the simple. And how is it simple? I'm just looking at my textbook and kind of looking at all of them to see which one compares. Joyzepam, well, that's not quite right. That's not quite right. So I'd have to actually change the order of stuff. Okay, watch this. Watch this. I want to change it so that joyzepam is compared to anxiety-free and joyzepam is compared to the placebo. I'm going to go to drug. I'm going to double click this. I'm going to change the levels. Let's see. I'm going to click on that, and then I think that. Voila. Voila. Ho ho, ho ho, right? And so it's changed the order of my levels so that joyzepam is now my first level compared to anxiety-free and then placebo. And now with that simple contrast, because what it's doing is comparing the first to the second and the first to the third, that's exactly what I wanted for my contrast. That's all I cared about. I don't care about any difference, if there is any, between anxiety-free and placebo, perhaps as a planned contrast. And so I would look at this. I would say the difference between joyzepam and the existing drug, statistically significant. The difference between joyzepam and the placebo, statistically significant. So my drug outperforms both the existing drug and the placebo. Again, don't care about the difference here. So that would be the best contrast to look at here. Sometimes, though, you don't have an a priori, before you run the analysis, pre-registered hypothesis, in which case you would run a post hoc after the fact. That's what post hoc means. A priori is like before the fact. Post hoc is after the fact, basically. And so I could do a post hoc test for a drug. So I need to take that, move it over. And there are some corrections here, and you can actually look at all of this and note how the p-value changes to all of them. This makes the most sense of comparing to see what happens with the p-value, right? So the p-value for Tukey is a bit bigger, Chaffee is even bigger, Bonferroni is the biggest, the most conservative correction, and the Holmes test is the least conservative correction, the most liberal correction. I like to use just Tukey's. It's just the easiest to interpret, in my opinion. So I use Tukey's, and so you just explain that you do the Tukey post hoc test to look at the group differences. And you'll note that it compares all groups among all groups. We don't specify ahead of time what we're comparing. And let's make sure we ask for our effect size. So what's the difference between joyzepam and anxiety-free? Well, p-value is still 0.002, and our Cohen's d is quite big. Big difference. Joyzepam to placebo, again, statistically significant, and a big Cohen's d effect size. But is there a difference between anxiety-free and placebo? No. P-value is not statistically significant, even though we have a large effect size, right? And why is that the case? We don't have a big sample size. If we had a bigger sample size, this would become statistically significant once we have enough power to detect this effect size. Okay, that's it. Those how you do the planned contrast and the post hoc test to compare the group differences. So now we know that joyzepam, just kind of like what we thought, but we wanted to be sure. Joyzepam outperformed both anxiety-free and placebo, and there's no difference between the two. And so I have an example of how to keep going. I have an example of how to write up the planned contrast in APA style. So I don't think I specify specifically, but here's how you would write up the simple contrast. And then a post hoc test I have right here, how to write up that one as well. Okay. I give you the little formula of how to write up the F test. Remember, we round everything to 2 decimal places, except for the p-value, which is to 3. Okay. In case of violated assumptions, we have to change to the Games-Howell unequal variances. So let's do that real quick. I know this video is getting a little long, but there's a little bit here, right? We want to make sure we understand it all. Okay. The thing with the and I don't know if I wrote this very well in the So the thing with the ANOVA test is that you'll notice that there actually isn't. We can't specify like we want to run the Games-Howell, the Welch's F test, right? So unfortunately, if you don't meet the assumptions of normality or homogeneity of variance, you actually do need to go to ANOVA, one-way ANOVA. It's the only reason I would let you do this, because then you can say don't assume equal variances. It looks exactly the same. It's very simple. Mood gain goes into your dependent variable. That's why there's the ruler there. Continuous goes there. Drug goes into your grouping variable. And when you ask for post hoc tests, you'll want to make sure, if you have the assuming unequal variances, that if you're doing post hoc, you're doing the Games-Howell, because they'll also assume unequal variances when comparing the group differences. You can ask for all of this information as well. So it'll give you little asterisks if it's significant. You can also test for your assumptions and do your statistics. But notice that's it, right? We can't do planned contrast with this one. We only have a couple options with the post hoc tests. That's why I have you default to the other one. If you don't meet the assumptions, then you can do this one. Okay, that's it for the one-way ANOVA. Be sure you're adding a lot of questions, comments, that you're familiar with how to do this, because you're going to do it yourself for the homework.